very good morning, good afternoon, good evening to all my friends, students and participants for this NPTEL MOOC course, the title of which is Application of Forecasting, Regression and Time Series Models. And my good name is Raghunandan Sengupta from the IME department at IIT Kanpur. So, as you are all aware, there are three broad areas for this course. The first one being forecasting, second one is regression, third one is time series. And as I mentioned in the last lecture, it is basically the fag end of this regression models. This is week 10 and we will start lecture number 47. So, what is the coverage? Coverage is that we will consider different nonlinear regression models and we will discuss the examples using the PPT slides as well as the detailed simulations which we have in the Excel sheet, which will be shared with you. The next model which we will consider is the power curve model, which is the allometric equation which is given by this form. So, the equation is y is equal to theta 1 into x to the power theta 2, that is y is the power, plus epsilon, epsilon is the error, and if you remember, the error can be uniform discrete between -1 to +1, or the error can also be given as normal with 0 1, and for our discussion we are going to consider this error as uniform discrete -1 to +1. It can also be taken as -2 to +2, considering the variability can be increased, or can be taken from -3 to +3 or -4 to +4. So, the mean value remains 0, but the variability would increase depending on what you think the data and its fluctuations are. Theta 1 is the constant and theta 2 is the power of x and epsilon is the error term. So, this is the first plot. We are doing exactly the same thing, plotting for different combinations of theta 1 and theta 2 and then discussing in details using different type of simulation, which you can see as I simulate. Simulate in the sense all the data and the things have been input in the Excel sheet, you just need to change the theta 1 value, theta 2 value, or the seed value which is the starting value of x, or the delta x which is the increments of x which you want to do for plotting. And for all the data points, I have taken 124 data points for x, similarly plotted 124 data points for y, have the errors for 124 data points as needed, and based on the best fit line which is y added with the error, because error can be positive and negative, you will basically have the actual data which is y 1, and then we plot y and y 1 with respect to x, which is being shown here in the PPT slides. So, is the power equation where you are plotting y and y 1 versus x, and for the case of this one, the power equation we are taking theta 1 as 20 and theta 2 as 0.5, the power value of x is 0.5. And if you see, we will come to the Excel sheet later. If you see, the best fit line and the actual data points are fitting quite nicely. The increments of y or y 1 values along the y axis are given in increments of 20, 20, 40, 60, 80, and it goes on. And with this, if I go back to the Excel sheet, I will be better in a position to explain. So, I consider the power equation. So, let us take out the power. Yes, this is the graph. So, I have saved everything in the Excel sheet. When it is shared with you, you will understand. So, by the way, one thing which you see in the Excel sheet and the PPT, be aware the errors are being randomly generated. So, each time I open the Excel sheet or you open the Excel sheet, or basically simulate or change the starting values or change the theta 1 values, change the theta 2 values, the errors are being immediately computed in Excel sheet. So, they are not fixed. So, they change depending on the underlying distribution which is there, which is the case of uniform discrete with between -1 and +1. So, there you will check it. So, once you see the Excel file and the values of simulation, things would be absolutely crystal clear, but you have to spend time there to understand. So, for the case of the power equation, I am taking theta 1 as 20, theta 2 as 0.5. So, let me check 20 plus 0.5. So, I have this equation. So, error terms are given in column AC, the best fit line y is given in column AB, the values of x, because starting seed value of x is 2, increments of 0.5. So, the second value will be 2 plus 0.5 is 2.5, third value is 2.5 plus 0.5 is 3, next value is 3 plus 0.5 is 3.5, and it goes on. And the y values are corresponding calculated based on the power equation, which as you know is given by this. This is basically theta 1 into x to the power theta 2, where theta 1 is 20, theta 2 is 0.5, and based on the errors which have been randomly generated. I am considering here, if you check this one, it gives you random number which is generated between 0 and 1 into 2, that means it will be generated between 0 to 2 minus 1. So, that means you are bringing back the random number generation between minus 1 to plus 1, that is point 1. Point number 2 is that I multiply by 10, which means I am generating the random numbers between minus 10 to plus 10. So, you can change that 10 value which you are multiplying, you can change to 5. So, it will be generated between 5 to minus 5 to plus 5. So, just for information, if I take the error term, average value is, because it is simulated with data only for 124 data points, the average value comes out to be 0.25. Actually should be 0 in the long run, and the variability, if you consider, it is basically b minus a whole square by 12. B is basically, in this case, is plus 10, a is minus 10. So, plus 10 minus of minus 10 is 20, whole square is 400, 400 by 12. So, that will be the variability. Variability is quite large here, if I consider. So, that would be coming out to be like 12 3s are 36. So, it will be about 33, which is quite high. I can reduce that rather than multiplying by 10, I can multiply it by 3. So, it will be generated between minus 3 to plus 3. So, the value of the variance would be plus 3 minus of minus 3, which is 6, 6 square is 36, 36 by 12 is 3. So, it will be 3 now. In the other case, it was 33 variance, now it is 3. So, you can change the concept of variability to get a whole gamut of simulation. Anyway, let me come back to this data point which I have. For the power equation, I am taking this error between minus 10 to plus 10. The y values are plotted in column AD, and this is the graph. So, if you see, they are dispersed both on the left hand side and the right hand side of the best fit line. So, here they are, because due to the simulation case, they are more skewed to the left. So, obviously, you can do a different type of simulation considering the errors are more skewed to the left or more skewed to the right, depending on how the data is there. So, the next graph, which is basically for theta 1 plus 0.2, theta 2 plus 0.5 plus 0.2, then theta 2 is 0.5. If you see this graph, so this is the data which you have for the graph, where theta 1 is also low, theta 2 is also low. So, in this case, it shows equally dispersed, there it was basically dispersed to the left, depending on how the simulation has been done. But actually, if you keep simulating, they would be, in the long run, the dispersion both to the left and the right should be equal, such that the average value of the error should be 0. So, here y is the best fit line, the blue one, and red one, y 1 is basically the actual data, which is for the simulation case. If you remember, I have just added or subtracted depending on the error is positive or negative. I have done it for the case for the with y and got this simulated data points. Now, if I go back to the value of theta 1 as 20 and theta 2 as minus 0.5. So, theta 1 is 20, just keep checking the graph, and this is minus 5, you will have this graph. Again nicely dispersed onto the right and left. So, here it is onto the left because they are skewed, but generally if I keep simulating the points, they are equally dispersed to the right and left. Now, actually what we are doing is, for all these cases, for the rectangular hyperbola and then for this power equation or for the logarithmic one, which is the second example, we are aiming to minimize the square or the errors, which is the basically the so called variability, and trying to minimize the error is basically the difference between the actual value and the best fit value. An average, if we try to minimize, is exactly equal to the concept of trying to minimize the variability, which is the second moment, and that is the crux of the discussion which we had from day one when we started the forecasting models. So, with the value of 20 of theta 1 and theta 2 as minus 5, we have this data. Then if we have the data fit, when we have theta 1 as minus 200, theta 2 as minus 0.5. So, if we have again equally dispersed both on the left and the right, and in this case let me check, wait 200 and minus 0.5, minus 200, sorry, my mistake, minus 200. So, the data would exactly mimic. Again here in this PPT is more skewed to the left, but in the simulation one I have been able to do that for a long time for a large set. They are the instances based on which the simulation has come. So, if you keep simulating such 124 data points 1000 times, you will have 124,000 data points, which will be 1,24,000. So, 1,24,000 is a huge data set, which will give you a good idea that what is the error distribution, the mean value of the errors, and so on and so forth. Now, we have considered the rectangular hyperbola, the logarithmic one, and the power one, and for all these things we have been changing the values of theta 1, changing the values of theta 2, and later on we will see there would be another set of nonlinear regression models where there is 3 parameters, theta 1, theta 2, theta 3, and we will explain that. And I did also mention the seed value of x, which we have kept fixed, but it can be changed, the increment value of x, which we have kept fixed, but it can be changed. So, in this third model, which is example number 37, let us basically simulate the data, and for all 4 different combinations of theta 1, theta 2, which is there in the PPT slide, but let us try to check that with the changing seed value of starting value of x and a changing value of increment of x, how do the different sets of graphs pan out, how do they look? Do they look totally different based on the case when what the data sets which we have simulated for the case of the seed value of x. Say for example, I am only going to concentrate for the power equation first, where the seed value of x is given as 2 and the delta values is given as 0.4. So, for clarity in this Excel sheet, let me make the seed value of x as yellow. So, people can understand that the seed value can be changed accordingly, which I am trying to highlight in the Excel sheet. So, once you get the Excel sheet, you will understand. So, let us consider the power equation with the case of this fourth case, minus 200 of theta 1, minus 0.5 for theta 2, but with the seed value of x is now, say for example, 10, but delta value remains 0.5. So, how does it look? The properties of the graph does not change. So, they would look like slowly increasing at a higher rate and then asymptotically becoming coming back to the values which we have considered. So, if I consider the delta value as 10, say for example, seed value is also 10, delta value is also 10, that will increase for 10, 20, 30, 40 and go on. So, again the characteristics comes out to be exactly the same. So, which means it gives us lot of confidence in the simulated data points and simulation which we are doing in this Excel sheet are correct, which means that it will give you a huge gamut or huge set of simulations we can do in order to understand that. Similarly, if I do for the case of seed value of x as 10 and delta as 10, let us go back to the other starting value of theta 1 20, theta 2 as minus 0.5. So, theta 1 as 20, so it was plus 20. So, this is the graph, and if you see the graph, it is again same characteristics. So, it increases our confidence, increases our belief that the Excel sheet simulations are absolutely perfect. So, if I go to 0.2 for theta 1 and 0.5 plus for theta 2, so again the graph looks like here. Characteristics shape looks this, they may have a little bit more asymptotic or more curvy, but the general characteristics remain the same. So, if I consider 20 and 0.5, so here with the graph again same character. If you see another thing, the shape is same, the asymptotic is same, and also the error terms are behaving almost the same. Obviously, errors would change for each simulation, but the behavior, that how close they are to the best fit line, how far they are from the best fit line, are important things to watch for the simulations based on theta 1, theta 2 being changed, delta x being changed, seed value of x being changed. So, if I go back, and similarly you can do for the logarithmic one and the rectangular hyperbolic one, but let us continue, there are more such nonlinear regression models to consider. Now, let us come to the negative exponential model, which is given as theta 1 into in the bracket negative exponential, because the multiplying factor is 1 minus exponential part, 1 minus exponential theta 2 x, and obviously, this is an error term. Theta 1 is the multiplying factor, theta 2 is the power of x in the exponential term. So, let us now check the simulation data. This is the one snapshot for considering theta 1 as plus 2 and then theta 2 as plus 0.2. So, here the data sets of the simulated one is given, negative exponential theta 1 theta 2 given, delta x is 0.1, x is 0.1. So, it increases 0.1 to 0.2, 0.2 to 0.3, 0.3 to 0.4 again on 124 data points. Similarly, column AF is the y value, which is the best fit line. Errors I simulate between, if you check AG column is simulated between -1 to +1, and y1 is basically the actual data, which basically considers the best fit line with errors being added subtracted depending on the error terms are negative or positive. Now, let us check. So, plus 0.2 and plus 0.2. So, here the graph would be. So, this is the negative exponential. Let me take out the graph. Negative exponential, this one, this graph. So, for a value of negative exponential, I have to go more to the right. Yes. So, it was 2 and 0.2, both being plus. So, here you see the graph. So, there is dispersed both plus and minus, y is the best fit line, y 1 is red dotted one is basically the simulated data for based on the actual. So, the values plotted along the y axis, where we plot y and y 1 are increased in the quantum of 5, that is goes from -25, -20, -50, -10, so on and so forth. And x values, as you seen, have been plotted. And if I see here also the error terms are quite small. So, maximum to a value of 0.5, 0.6. You can check the error terms in the columns also, for column AG you will understand. So, now if I change for the second case, theta 1 as -2, theta 2 as +2, -2. So, it looks like this. So, again increasing. So, pattern remains the same. for all the simulation, which gives a lot of confidence that as I keep changing theta 1 and theta 2, the patterns would basically be mimicking each other. The errors would change because it is being simulated, number 1. And number 2, the dispersion of the errors would depend on the error concept we are adding, whether it is in uniform discrete between -1 to +1, or is it uniform discrete from -5 to +5, or is it standard normal deviate between 0 with the mean value of 0 and a standard deviation of 1, or a normal distribution with the mean value of 0 or a standard deviation of 5. So, that you can check and you can basically plot it in the errors and basically get a huge set of ideas that how would the errors look like and how would the actual graph, which is the dotted red points with respect to the blue points, which is the best fit line would look like. So, with the value of -2 and theta 2 as +2, we get the graph as shown here, negative exponential, and the graph which is shown in the PPT slide also matches. Now, let us consider theta 1 as +2, theta 2 as -2. So, this is +2. So, again it curves down +2 and -2. Let me check. Okay, this should be -2. So, again it goes up as it is, but here they are more dispersed to the left because based on the simulation. Here they are dispersed both onto the right and left. So, in this case, in the PPT slide, if you consider the mean value of the error is 0, and if I consider in the slide for PPT in the Excel sheet the mean value is 0, sorry, and in the PPT slide I have purposefully taken the mean value being more shifted onto the left or the right. So, if this case of the mean values are there, which means errors are positive. So, that means I am considering the average of the errors are positive, average values. You can similarly do it for the negative values also. So, that will give you a good idea that considering errors mean value is 0 or errors mean value being negative, errors mean value being positive. Now, you may ask the question why I am doing that for errors mean value being negative or why I am doing it for errors being positive. It is just a simulation work, but the actual idea based on which we will actually do it and which you can play with the data set in this simulation is basically consider the error values in the long run average is 0. That is what the assumption is, but as I wanted to give you a whole set of ideas, that is why I am doing the simulation with different mean values of errors. So, theta 1 plus 2 theta 2 minus 0.2 gives you the same type of idea. Now, if I consider the case of theta 1 minus 2 and theta 2 minus 0.5, let us see. So, again downward sloping as it is here also, there are these errors which is shown in the PPT slide are more positive average values, and in this case they are dispersed both onto the right and the left, that means the mean value is 0. So, again we get a lot of confidence in trying to simulate the data and get that idea. The next model which we consider is the asymptotic model, which describes limited growth where y approaches a horizontal asymptote as x tends to infinity, and it is given by y is equal to this line. This is the line. So, where it is theta 1 minus in the bracket theta 1 minus theta 2, the difference of these parameters in exponential theta 3 to the minus theta 3 to the power x. So, there are 3 parameters theta 1, theta 2, theta 3. Theta 1 is the maximum attainable value of y, theta 2 is the value of y when x is equal to 0, and you will see that in the Excel sheet, and theta 3 is the proportional factor relative rate of y increase while x increases also, and epsilon is the error term as already mentioned, and it will be repeated for each model. So, now with this I slowly consider the graph. So, here I am taking asymptotic values of theta 1 as 2000, theta 2 as 5 and theta 3 as 0.1. So, let us go to the Excel sheet and also open our case of the values of the consideration. This is the power one. We have considered the rectangle hyperbole, we consider the logarithmic one, we have considered the power one, we consider the negative one. So, now is basically asymptotic. Asymptotic would be there, I have said yes, it is there. So, this asymptotic one we will now consider. So, I will take this graph to the right, because all the graphs are being simulated based on the data. So, they will keep changing. So, it is asymptotic one, I take it here, yes, done. So, here also as we have considered the I am highlighting the cell where the seed value of x is. So, it is easier for all the candidates and the students who are taking this course, they can very easily use this Excel sheet. So, for the asymptotic one, this is the case, this is one of the instance I will come. So, I am considering theta 1 as 2000, let us consider, then theta 2 as 5, done, and theta 3 is 0.1. Here the starting value of x is 1 and delta value of x is 2. Errors are between -1 and +1, error is very small, and as the actual value and the difference between the actual value and the best fit line is very small, let us for simulation case increase the error such that the difference between the blue line which is the best fit and the red points which are the actual points would be much more stark. So, I will multiply with 10. So, it can be generated, let us multiply with 20. So, it will be generated between -20 and +20. This curve should be coming. Oh, I do not think I have, I will try to do that. So, I think the blue one so they are almost overlapping. So, let me do one thing, let me increase the error for better visibility. So, this I am doing a simulation, so I can definitely do that. Now, it makes sense. So, if you check this graph here for a theta 1 as 2000, theta 2 as 5, theta 3 as 0.1 and the error being simulated between, just this is a theoretical construct, between -100 and +100, that means error can be, the variance can be quite high, but the mean value remains 0. And if you see is asymptotically slowly increasing and the error terms are also low with comparison to the actual data and the best fit. So, here the asymptotic one, but more they are on to the left, because I have taken purposefully some errors which are more positive, average values more positive. So, if I consider starting value of x, so which is also interesting, let us consider starting value of 5 and a delta value of 2. So, you can see how the graph is changing, but the general pattern remains same, number 1, and the error terms are almost of the same quantum, plus minus, average value is 0. Variability is very high, because I am generating between -200 and +200, but as you give different values, you get a huge amount of set of information. Now, if I generate the data for 2005 and 0.5, so this is 0.5 for theta. So, this is almost a straight line as it is, but here it is more skewed to the left. There in the Excel sheet, they are dispersed both positive and negative. Let me check. Another thing, yes, this is important. Another thing is, I need to check, yes, this theta 1 value which I am taking as 2000 is the asymptotic value. As x tends to infinity, what is the y value? Let us check. See, maximum value of y is turning out to be 2000. So, asymptotically it goes to theta 1 value, which was mentioned in the PPT slide, where it was mentioned here, this point. maximum attainable value of y, and theta 2 value is the value of y when x is 0. Let us check. So, let me take the starting value of x is 0, and should it be 5? Let us check. Should it be 5 means this cell value which is AJ 149, this one. Let me highlight it with, say for example, orange for the time being. So, as I change to 0, what happens? See, it becomes 5, as it has been mentioned that theta 2 value would be the value of y as x is 0, and theta 1 is basically the asymptotic value of y as x tends to infinity, and that is matching with the simulation and as being mentioned. Now, let us go to value of 550 of theta 1. Let me take it as 1, delta value is 0.5 for the time being, just for explanation, and theta 2 is 20 and theta 3 is 0.5. So, you check this graph, this exactly matches what is being shown here. So, I am double checking the PPT one with the Excel sheet. Last one is 1000 for theta 1, let us change this to 1000. Theta 2 would be 4 and theta 3 is 2 plus 2.5. So, if I check, this is the graph and it exactly mimics what you see here. Also, let us check this 1000 value, is it the maximum value of y as x tends to infinity? Yes, it is matching. So, we are good. If I check x as 0, does it match to theta 2 which is 4? Wait. Oh, it should be 0. Yes, it matches. So, for 4 we are double confirmed that all the simulation runs are perfect. So, with this we will end this class where we have discussed two different models in details, asymptotic one and the one related to the negative exponential, and in the 46th, which was the previous lecture, we have discussed the logarithmic one and the power one. And we will continue discussing more such simulations in details in the subsequent class. Have a nice day and thank you very much.